Hello and welcome back. In today's video, I'm going through a Wilson mirror circuit, basically how it operates and what the current flow and everything looks like. Maybe we can get to an equation that tells you the programming current as well as the output current, look at some of the voltages that are present in the circuit, look at the current and basically just the general operation. Obviously, we can briefly talk about the applications as well, so where it's used. So the reason for this video is just basically to build an understanding of transistor circuits. I guess the more you look at them, the more you will understand how they operate, how they work, and when you see a circuit in front of you, you know how to analyze them. Also, we are at a point in Art of Electronics where we are doing exercise 2.18, and for that exercise we need to look at our Wilson mirror circuit in more detail, and we need to get to some equation that the question is asking us to do. So this will be a good preparation for that question as well. So firstly, I'm going to show you a basic current mirror circuit and then show you a Wilson current mirror, which basically removes some of the disadvantages of the basic current mirror. Let's get started. On the screen now, you've got the basic mirror circuit configuration using PNP transistors. As you can see, we have a pair of PNP transistors, Q1 and Q2. These are typically matched so that their gain is very similar and their VBE is also very similar. So a current mirror is a circuit designed to copy or mirror, as the name implies, one branch of the current to the other branch. So let's say we set our current using some device over here, then the current in this branch will be equal to the current that's flowing into this branch over here. You can also build this circuit up with an NPN transistor as well, where you would just basically turn everything upside down. There are plenty of examples available online if you want to have a look at NPN configuration as well. So in this example, this is the kind of the reference transistor, and then this is the mirror transistor. The emitters of both transistors are connected to the power supply. This is typically called the VCC. Another thing you will notice is that the base of both transistors is tied together, and the base of the transistor connection is also connected to the collector of our reference transistor, let's say Q1. So both of these transistors share the same VBE voltage. So here's how the circuit works step by step. So a reference current, Iref, basically going down this path, is established by connecting this resistor over here. And you know the voltage on this node over here due to the power supply. So obviously this would be a known power supply. Let's say is 10 volts in this case. So you have 10 volts over here. You're going to have a VBE voltage drop here. So let's say that's 0.6. Then that means that the voltage on the base junction over here is going to be 10 volts minus 0.6. So that gives you a voltage of 9.4 volts over here. And you can see that the base and the collector are tied together. So the voltage on this node here is also going to be 9.4 volts. Now, obviously using Ohm's law, you can calculate what your current in this path is going to be. So if you have 9.4 volts, you basically do 9.4 volts divided by the current that you want to go through this path. And that gives you the programming current for the circuit. Let's say we set this power supply to 10 volts. We are going to have a 1k resistor over here. So that should give us a current that's basically 9.4 divided by 1k. So that's approximately 9.4 milliamps flowing in this direction over here, assuming there's a 0.6 volt drop on this node, or the VBE voltage is 0.6 volt. Now, since the Q1, the reference transistor, and the Q2, the mirroring transistor, share the same base emitter voltage, assuming the transistors are matched, the collector current in Q2 will also be equal to the collector current that's going through this junction over here. So in an ideal case, basically the Iref, which is this junction, is equal to I out, which is this junction over here. So I'm going to call this our load resistor, and let's put a value of 1 kilo ohm there for now. The key point here is that the current in the second branch, so this branch over here, is controlled by this branch over here. And obviously we can control that current using R2 and a known power supply voltage, which obviously makes it very useful for providing a stable current in various parts of a circuit. So the advantage of a basic current mirror is that it's widely used, obviously, and it needs one less transistor than the current mirror that I'm going to talk about next, the Wilson mirror. Obviously, you can see the circuit is quite simple. It's very easy to understand. You can see what's going on. You know, you only need 2 transistors and 1 resistor to build up a current source, basically. And one of the disadvantages of this current mirror is that if you want the current mirror to work perfectly, these 2 transistors Q1 and Q2 must be perfectly matched in terms of characteristics, specifically their base emitter voltages. Obviously, in a real world circuit, that's going to be different. So the transistor mirrored currents will be slightly different, and the difference will depend on obviously your variation between the 2 transistors. Another problem that we have on this circuit looking at the current. So you can see for a PNP transistor, there's a current flowing in this direction, but there's also current coming out from here, flowing down to here. There's also current obviously flowing from this direction down to the load resistor over here, but then there's a small amount of current that's flowing in this direction. If you look at your NPN transistor gain or current gain, it's basically IC, the collector current, which is flowing out from this junction, and this junction is equal to the base current times the gain of the transistor, which is typically known as beta. So let's say we have a gain of 100 and we're trying to get 1 milliamp down this path, then that means we're going to have 100 microamps flowing out from the base. Because this is PNP, the current is flowing out from the base. For an NPN transistor, the current would be flowing into the base. So you got 100 microamps flowing out here. You got 100 microamps because the current is being mirrored, obviously. So you got 100 microamps flowing into here. That current basically flows down this path over here. So the current through R2 is going to be IC plus IB1 plus IB2, and the current through the load resistor is just going to be IC2, which is equal to this current over here. So you can see that there is a small difference, or approximately in the example I gave, 200 microamp difference between the reference current and the load current, in that the reference current is going to be slightly higher. Now in this circuit, this isn't compensated for. We're going to look at the Wilson mirror next, where we take this into effect, where basically the Wilson mirror tries to remove that error, and we'll talk about that in more detail soon. Another issue with this type of transistor circuit or this type of basic mirror is the effect from something called the early effect, which refers to the slight variation in the transistor's collector current due to changes in the collector voltage. Now this effect basically reduces the accuracy of the current mirror slightly, especially when the output voltage changes. Basically this is saying the output impedance is not infinite, and that's because of the slight variation of VBE with collector voltage. So you can look at more detail in the book or online if you want to for this, but yeah, it's an important effect to understand for NPN on PNP transistors. Another issue is the limited output resistance. So the basic mirror circuit that we have on the screen now has relatively low output resistance, meaning that if the load voltage changes, the output current will slightly change as well. This limits the precision of the mirrored current, and the working range. So obviously it's a very simple circuit, but it has loads of uses for voltage references and biasing circuits and basically other op-amp type circuits in analog electronics. So yeah, a very useful circuit to learn and understand how it works. So if a better current source is needed, then we can use something called a Wilson mirror. So this is a enhanced version of the basic current mirror circuit that we just saw, and it basically aims to improve the accuracy and the output resistance, two of the limitations that we spoke about in the basic mirror circuit. Now you can see that it uses 3 transistors, as I said before. So in this circuit, the third transistor helps to compensate for the base currents that we spoke about before. So if you remember previously, the base currents were flowing through the programming resistor, or the resistor that was setting the mirroring current. Now in this circuit, you can see that the base current is flowing to the emitter of the third transistor. So let's quickly talk about how this circuit works. What we're going to do is ignore R5 and R6 for the time being. So let's say we have a power supply of 10 volts over here. So that means that we're going to have 10 volts on the emitter junctions of both Q4 and Q5. So these two transistors again need to be matched so that they're going to be equal. So you have 10 volts over here. You have a VBE voltage of 0.6, let's say for both transistors. That means that the voltage over here is going to be 10 minus 0.6, so 9.4 volts. And that means that the current flowing through this junction over here is going to be the collector current plus 2 times the base current, basically, because the base currents are going to be equal. The voltage on this junction is going to be 9.4 volts as well. Now if you look at this transistor over here, you can see you're going to have a 0.6 volt drop over here. So what we're going to have, you're going to have a 0.6 volt drop over here. So this is going to be 10 minus 2 times the VBE voltage. So let's say you have 0.6 voltage drop here, 0.6 over here. Then this is obviously going to be 8.8 volts. And using that knowledge, you can calculate the setting current for this circuit. So if you have 8.8 volts over here, then you can basically choose a value for the resistor such that you get the current that you want from this junction over here. Obviously, you're going to have a little bit of current flowing in this direction. Both Q4 and Q5 have fixed emitter, which is over here, collector voltage drops. And you can think of Q6 down here simply as passing the current through a load that varies, basically. Now, the book says that the transistor Q6, or in the book as Q3, does not need to be matched to Q1 and Q2. Q2, or in this case is Q4 and Q5. But if it has the same beta, then you're basically going to get an exact cancellation of the base current errors that I just spoke about, in that you get a current flowing down this direction. So for the question, exercise 2.17, I'm basically going to show you how to calculate that, and obviously that video will be coming out next. Now let's quickly just talk about the two resistors that were present when I first showed you this circuit. So both of these resistors can be used to unbalance the emitters of the two matched transistors, and what that lets you do is generate basically a current, the output current, that is a proportion of the input current, or a multiple of the input current. So if you have, let's say, 1 milliamp over here, you can get 1.5 milliamps going through this junction. It does mean that you need to make sure that you're accounting for the difference in the VBE voltage. If you look at the art of electronics, you can see a nice figure, basically figure 2.62, which shows you how you can account for the collector current and how the VBE changes with the collector current. What I'm going to do now is just quickly show you simulations of the two circuits I spoke about. So firstly, the basic current mirror. You can see that we have a 1K resistor over here. We're going to have roughly 9.4 volts over here. So I'm just going to move this up to 10.6, just so that we have a nice current, or nice readable current, flowing in this direction. So if you have 10.6 volts here, remember that we have 10 volts over here, and this is also going to be 10 volts. We have a 1K resistor. That means that there's 10 milliamps flowing through this resistor. There should also be 10 milliamps flowing in this direction as well, due to the matched transistors. So let's simulate that now to see what's happening. So first of all, you can see that obviously we didn't get a perfect 0.6 volts drop here. We in fact have 832 millivolts, not 600 millivolts. So what I'm going to do is just basically change this up a little bit more, in that 8.23 or 832. So now we should have 10 volts over here, or approximately 10 volts over here. So 10.8 volts here. We have a VBE voltage of 0.8. So you get 10 volts here. That means that you're going to have 10 volts in this junction over here as well. Hopefully the lines are clear to see. Otherwise I can try and increase the line size a little bit, see if that helps. So hopefully that is better. Let me also try to increase the font size. So again, you have 10.8 volts from the power supply, and obviously I've just set that to get a nice value on the resistor. You have 10 volts on the base voltage of the matched transistors. So that's because of 832 millivolts drop on the base emitter junction of this transistor. And you have 10 volts on this as well. Now we put a 1K resistor down here, so that we have basically 10 milliamps flowing through this. And that is just using Ohm's law, basically V equals IR. So we have a voltage of 10 volts divided by 1K. So we have 10 milliamps flowing in this direction. That means we should have approximately 10 milliamps flowing through this junction as well. So you can see it's just slightly under 10 milliamps. So 9.8 milliamps. Now we also discussed the current that's flowing through here. So you can see there's approximately 100 microamps flowing from this direction. There's approximately 100 microamps flowing from this direction. And both of those are flowing into this resistor over here. So this resistor, or the current through this resistor, is going to be slightly higher than the current through this resistor, as you can see on the simulation. So the current through this resistor is approximately 10 milliamps, whereas the current through this resistor is approximately 200 microamps below that. And that is because of the base currents that are flowing through our programming resistor. So one of the things about the current source, we can vary this load resistor and still get the same current flowing through it. So let's do that now. So I'm going to try a 500 ohm resistor, and you can see that the current flowing through it is still the same. Now I can try slightly higher, but I'm not sure if the voltage limits will basically hinder that. So 9.8 volts, obviously we're quite close to the power supply limit. So if you try to go anything higher than 1K, then that's probably not going to work, as we're going to saturate against the power supply. As you can see that the current is starting to drop, and that's because this is going to be saturating. So there's approximately 0.2 volts on this transistor VCE junction. So that's the E junction, that's the C junction. So there's going to be at saturation approximately 0.1, 0.2 volts on this. And you can see that on the simulation over here. So you got 149 millivolts. Basically this transistor is in saturation. Now we can help that if we vary the power supply, but you'll see that that has a effect on the circuit as well, which is another limitation I didn't discuss during the kind of the initial presentation of the circuit. But we can reduce this further. So let's try 200 ohms. And if you look at the current flowing through it, you can see that it's still, 10 milliamps and it's still mirroring what we set. So we have some current that we set over here because of our known voltage source, because of our known transistor characteristics. We set up a programming current and we got a same current flowing in a different path, basically because of our matched transistors. So you can see how useful this circuit can be. And obviously it's used a lot in biasing circuits, voltage regulators and things like that. Now, one of the things I spoke about was the limitation of the voltage source. So in this case, we had obviously 10 volts and I said we're saturating at 1K1. So we're not maintaining our 10 milliamps properly as the current through it is starting to drop. You can see that it's dropping to 9.72 rather than 9.8 that it was previously. And that is obviously because the transistor is saturating, as I mentioned before. Obviously, you can try and help that by increasing the power supply. So let's say we go for 15 volt power supply. But one of the things hopefully you notice now is that we have changed our programming current. The programming current is directly dependent on our power supply. So we have 15 volts over here now. We're going to have a 0.8 volts drop on this junction over here because of this transistor base emitter voltage. So we're going to have 14.2 volts approximately on this junction here. So that gives us 14.2 milliamps flowing through this resistor. So obviously you can see that it's no longer 10 milliamps that we previously set. So if your power supply varies, basically this circuit is not that useful. There are things you can do to go around this. Obviously you can set this junction up such that it doesn't vary with the power supply, maybe with a then a diode or something like that, or maybe you have a regulated power supply input. But yeah, that's something you should be careful with. So hopefully that makes the operation of the basic current mirror simplified for you guys. If you have any questions, obviously please let me know in the comment section below and I'll be happy to help. What we're going to do now is move on to looking at the Wilson mirror circuit and basically look at how that is different to this circuit over here. I am going to remove these two resistors because I think a simpler circuit will be easier to understand. So let's do that now. So adding the wires back in, I'm pressing the E key on my LT Spice because they've recently changed all the key binds and it's very annoying. So pressing the simulate button now, you can see our programming current. In this case, we have 10 volts over here. We're going to have 2 VBE voltage drops before we get to this junction. So we're going to have a 0.6 or maybe 0.8 volt drop over here. So that's represented with the red line. You're going to have another VBE voltage drop over here. So that's 830 millivolts as well. So over here on our programming resistor, the current programming resistor R3, we're going to have a voltage of 10 minus 1.6 volts. So you can see it's roughly 8.4 volts in this case. Now 8.4 divided by 1K, that gives us a programming current of 8.4 milliamps or maybe 8.3 milliamps looking at the number carefully over here. So looking at the current through it, we can see that we've got 8.3 milliamps flowing through R3 and we should have the same current flowing through our load resistor R4. So just clicking on that now, you can see it's very similar. What I'm going to do is try and make this such that we get approximately 10 milliamps. Then we can look at if there is a difference between the two circuits. So let me change this to 11.6 volts, change this one back to 10 volts. So you have 9.1 volts over here. So that's because of this emitter voltage drop, which is 831. And you have 9.9. So a slight difference. Let me try to remove that difference. So now you can see I've changed both the power supplies such that we get a nice approximately 10 volts drop on our programming resistor. So this one is at 9.992 and this one is at 9.999. So a small difference of approximately 7 milliamps, 7 millivolts. So that shouldn't matter. But we can see that our programming current is 9.992 and 9.999, so approximately 10 milliamps in both cases. And we can look at our output current. So this is the output current on the basic current mirror, and this is the output current on our Wilson current mirror. So you can see it's closer to 10 milliamps as we were expecting, and it's not 200 microamps different that we saw on our basic mirror over here. Obviously the programming current is set slightly differently. This does suffer from the same limitations of the power supply. So if I was to change the power supply on this circuit, then our programming current will also change. But to set up a current you basically need to calculate the resistor value using Ohm's law. So it's really as simple as that. And obviously, if you want to have a voltage source independent current source, then you can put in a Zener diode or something like that to make the voltage fixed so that your current is fixed as well. Now we can also, similar to the other circuit, we can vary our resistor and we will basically get the same current but with obviously different loads. So we have 1k load on this side, we have 200 ohms on this side, but they both are giving us 10 milliamps. So it's a very good current mirror in terms of that. And most of the time you probably are okay with the basic mirror, but sometimes this can offer you the better accuracy if you need it. And it's not that many more components. As you can see, it's only one more transistor for the circuit. So hopefully you found that useful. I'm just going to show you some examples of where current mirrors are used. And I don't know if you guys know about this, but electrical stack exchange is a very good source of information if you want to check out some, if you want to ask questions. But obviously make sure you ask your questions well. It does help with getting responses properly as well. And obviously make sure you show that you've put some effort into your questions that you're asking. Otherwise, you can't expect something back if you're not putting the effort in. So here are some examples of where current mirrors are used. Obviously, this one's a little bit more complicated, but you can find some examples where they're used, but mainly in basically amplifiers. So you can see the current mirror circuit down over here. You've got a differential amplifier over here. In this circuit, your current mirror is down here. Oh, this one's interesting. You can see that they've used a current mirror to drive the one of the voltage threshold pins. I think that is. I've not used a 555 timer for a very long time, but you can see that this capacitor is going to charge at a fixed rate. You set up a current over here, and the current going through this resistor and into this capacitor is going to be fixed. You basically negate the capacitor charging curve, the exponential, and you can get a linear line with a fixed input current, I think anyway. I'm just analyzing that from the top of my head. If you were to draw this out, I think the voltage on this capacitor would look like a linear line rather than your typical capacitor charging curve. But yeah, I'm not entirely sure on the pinouts for this 555 timer, but it's an interesting application, and maybe you can simulate it on LT-Spice as well to see how it works. I think all of this is really good to understand the basic operation of this circuit for the Wilson mirror and the basic current mirror. So you're probably unlikely to need the Wilson mirror, but it's good to know anyway. So hopefully you found my circuit explanation useful. If you have any questions for me, please let me know in the comment section, and yeah, I'll be happy to help. Don't forget to like, comment, and obviously subscribe if you want more of these videos. And the next video will be on art of electronics exercise 2.17, and obviously I've got that all figured out now, so I'll be sharing the solution soon.